Good afternoon, folks. Welcome. Happy Thursday.
Thank you. Same to you.
Thank you. So I'm here. I am in Santa Barbara teaching because my daughter is graduating from college on Saturday. So we came up here to just get ready. So anyway, there's one advantage to things being remote, because otherwise I would have been driving late.
We should be seeing the beach instead.
I thought about that, but I didn't want to make you guys too jealous. So I will be going to the beach tomorrow. Okay.
Okay.
Anyway, how are things going? Did anyone
I just did. Yes, I did.
quiz?
Yeah, I have a problem with the timer. I was never able to see the time that was running.
Oh,
So I was running. I was blind in as far as time. So at the end, I had an error in my sign, and I said, okay, if I try to fix it, I'm I'm risking to just run out of time. So instead, I wrote a note for you because I might have time. I don't know, but I just I couldn't just try to fix it. I knew what it was. I knew why I got the wrong sign, but I just said, I'm not going to risk trying to fix it when I don't know the time.
yeah.
But I ran a note for you in the quiz. Hopefully
So
you can.
did anyone else have a similar problem where they couldn't see the time? I'm just curious if this is. Oh no, you just clicked on it, it does, and you don't know if you started it. Boy, that's weird. Okay, well, I'm gonna have to look into that. So
Yeah, from a while I thought I was I thought I was drawn a section at the end of it. So when I was trying to see what it was because I didn't see anything.
Well, there were some other weird things that were going on, like on my end when I was trying to create the quiz. So I don't know if if Gradescope did some changes and it had some weird effects, but
yeah, just give me all the points. That's it. That should fix it.
Yeah. So yeah, I could send them a message anyway. Okay, anyone else have any comments or questions? Okay, so the rest of you, if you don't have a timer, why don't you just have a timer? So, and Kevin, if it turns out they don't let you take the quiz or whatever, just let me know and we'll try and figure out how to make that work. Okay. All right. I think we can make it work if they, for some reason, it's going now. Okay. So today, just want to do one more example from 6.2, and then I want to start talking about parametric curves. So, and I've got to do it slightly differently these days. I'm not quite sure why, but I wasn't able to just share my screen, so I have to join in and do it that way. Okay, so this is 2310-04 on May 6th. Okay, so let me remind you where we were last time. We had talking about orthogonal sets of vectors, right? So last time we had orthogonal sets. And that means that any two set in, if you take the dot product of any two vectors in the set, you get 0. So that just means that every pair of vectors is orthogonal. Or another way to say it is every vector is orthogonal to every other vector in the set. And then we had orthonormal set, and an orthonormal set. Sorry, I spelled that wrong. Orthonormal set And that's where the length of, it's an orthogonal set, but the length of each vector in the orthogonal set is 1 unit. Okay, and we did some examples. And I had one example I wanted to do in addition to that. Okay, so I'm going to let W be the span of these two vectors, 1, 2, -3, and 1, 0, 2. And I think these are vectors we used in a previous example as well. So those are vectors in 3 space. Pop quiz, is that a basis for W? So pop quiz. Those two, is that a basis for W? Anyone remember the properties of a basis?
It's a spanning set and it's linearly independent.
Yeah, that's it. Okay, so pop quiz. Is this a spanning set for W?
Should be.
Let me remind you what a spanning set is. A spanning set means that if you give me any vector in W, I can write it as a linear combination of those two vectors. So if I give you a vector in W, can you write it as a linear combination of those two?
Yes.
Yeah, because that's how we've defined W, right? W is the span of these guys. Remember that the span of a set of vectors is by definition the set of all linear combinations of those two vectors, right? So anyway, I'm not going to try and put that last curly Q on there. What that means is just by definition, any vector in here has to be a linear combination of those two. So they do span. So these two vectors span W by definition. Are they linearly independent? That's
They
the
better
other
be.
property.
Yes.
Yeah. Now, how can you tell if two vectors are linearly independent? Or linear, maybe it's easier to see if they're linearly dependent. If they're dependent, then they have, if two of them, right? Not a lot, but if there's exactly two vectors, how can you tell if they're linearly dependent?
If they are multiple of each other, that means they are dependent.
Yeah, that's the only way. Okay, I give you two vectors, they're linearly dependent if and only if they're scalar multiples. So are these two scalar multiples? Is there one number I can multiply this first vector by to get the second vector?
That's 0.
Well, if I multiply it by 0, do I get the second vector? Because I have to multiply every entry by 0. If I multiply it by 0, then I get the 0 vector, which is different from that one, right? So these are not scalar multiples. So they're linearly independent and because they're not scalar multiples, so linearly independent because not scalar multiples. And they span by definition of W. So that implies they are a basis for W, okay? Any questions about that? That's not a bad, the reason I went through all that is, well, because we need it shortly, but it's just not a bad review. You know, we've only got one more week of classes left. those are lots of different concepts we talked about, and it's been a while since we talked about them, but they're concepts that will be on the final exam, so it doesn't hurt to just refresh them every now and again. Okay, so that's a basis. So here's another pop quiz. What is the dimension of W? Anyone
was
remember?
3.
Go ahead.
3. No.
Well, does anyone remember what?
Well, we had
the
2 vectors. It's
dimension-
2 then.
Sorry. Anyone remember what the dimension of a vector space is? Subspace. How do you find the dimension of a subspace? It's the number of vectors in any basis. So the dimension of W is the number of vectors in any basis. So now what's the dimension?
2.
2. Yeah, because here's a basis for W consisting of 2 vectors. What that means to me and to you is that W is a plane in 3 space. Okay, so it's a subspace of 3 space that's a plane. Okay. Okay. That all of that was just a review of old stuff. So not last week, but a long time ago. Any questions about all of any of those concepts? Okay, that had nothing to do with orthogonal sets or orthonormal sets. So I have this W here, and what I'd like to do is find first an orthogonal basis. So my first goal is to find an orthogonal basis. For W. So I might just first ask you, is this here's a basis, is it an orthogonal basis? There's a basis right there, the 1, 2, -3, 1, 0, 2. Is that an orthogonal basis for W?
No.
Well, you had to test it, I guess. You had to.
So how would I test it? Yeah, I mean, that's a better question. How do I determine if this is an orthogonal basis?
You had to multiply it by itself. No.
So
Take the dot product.
yes, take the dot product, and it'll be orthogonal if what?
Equals to 0.
If the dot product equals 0. Okay. So I do hope you're getting comfortable with the dot product. Remember, we're just going to multiply corresponding entries and then add up those products, right? So it'll be 1 times 1 plus 2 times 0 plus -3 times 2, right? So it's going to be 1 minus 6 is -5. The dot product of this guy is -5. These two guys are -5. So they are not orthogonal. And we want to find an orthogonal basis. So this is our goal. And this will be just part A, I guess. Okay, and so here's the strategy. Since it's a basis, let's call this vector B1 and this vector B2. Okay, I just want to draw a schematic of what we're going to do. So B1 is some vector. B2 is another vector. Draw them so they share this. They both start at the origin, say. Okay. last time we did an example where we took like B2 and we wrote it as a sum of a multiple of B1 and a vector perpendicular to B1. Let me say that again. We wrote B2 as a linear combination of B1 and a vector perpendicular to B1. And remember that the way we did that is we dropped a perpendicular to B1, and where that hits B1 is the end of the projection of B2 onto L, and we called that, and the book calls that B2 hat. So our notation for that projection is B2 hat. And again, we get it by dropping a perpendicular from the tip of B2 down here, dropping a perpendicular from the tip of B2 down to B1. Okay, if you look at the vector from the end of B2 hat to the end of B2, so this vector here, let me call that B3. That vector was the one that's orthogonal to B1. Oh, what does orthogonal mean, by the way?
Perpendicular.
Perpendicular, yeah, it's just another word for perpendicular. So this B3, so what I've done in this schematic is I've written B2 as a sum of a multiple of B1 and a vector perpendicular to B1. Okay, and let's see if I can copy that. Rats, that's not what I wanted to do. Okay, I'm just going to copy all that. And I'm going to paste it here. And just move the whole thing up. Okay, so my claim is that B1, B3, just those two vectors, is an orthogonal basis for W. And I'm going to use, in order to convince you of this, I'm going to use another fact from back in the day, okay? So way back when we said, if you know the dimension of your space, then any set with that many vectors, so in our case, the dimension is 2. So any set with 2 vectors, if it's linearly independent, it will have to also span. Or if it spans, it'll also have to be linearly independent. So there was this theorem that said if you have the right number of vectors in your set and it satisfies one of the 2 properties required for a basis, you get the other property for free. Okay. What that means is for my B1 and my B3, that's 2 vectors in a 2-dimensional space. So I got the right number of vectors in this set. If they're linearly independent, then they also have to span. But clearly they're linearly independent in this schematic, right? So, because they're orthogonal, for goodness sakes, right? So they are not scalar multiples of each other. So since B1 and B3 are linearly independent, and actually maybe at some point I'll give you a quick proof that orthogonal vectors are linearly independent, because it's kind of a clever little proof. Anyway, since they're linearly independent, and the dimension of W equals 2, they are a basis for W. Okay. So this is the proof of the claim. So what that means is if I can, our original, actually, I don't even have to go back. I'm trying to find an orthogonal basis. If I can calculate this B3, then I know what my orthogonal basis is. So I just got to calculate B3. And the observation is that B3 equals, so remember, if you have a vector that goes between the endpoints of two other vectors, you can calculate it just by terminal minus initial, right? It's the terminal point minus the initial point. So that's the B2 minus B2 hat. Okay, and then I want to recall that the projection, the formula for a projection, right? So if I'm going to project B2 onto L, where L is the line containing B1, then it's going to be B2 dotted with B1 divided by B1 dotted with B1 times B1. This was that ugly, horrendous formula we got last time. And remember the way, the way I remember this is I've got two vectors, B2 and the vector I'm projecting it onto. I'm projecting it onto B1. So the B1 is everywhere except one slot, and the B2 goes in the upper left slot, if you will. And every other occurrence of a vector in that formula is B1. But this is not, so this is my B2 hat, right? So B2 hat, let me just grab the formulas from before. It's going to be B2, which was my 102, dotted with B1, which is 1, 2, negative 3, divided by B1 dotted with B1. And actually, let me remind you that if you dot a vector with itself, all you get is the sum of the squares of the entries, okay? So really not a big deal. The B1 dotted with B1 is 1 squared plus 2 squared plus negative 3 squared, right? And then you just multiply that times the vector 1, 2, negative 3. And what you should notice is the dot product in the numerator is going to be 1 minus 6, so that's negative 5. And in the denominator, I've got 1 plus 4 plus 9. 9 and 1 is 10, and 4 more is 14. So it's negative 5/14 times 1, 2, negative 3. So this vector that we just calculated corresponds to the green one here. It's the projection of B2 onto L. Any questions about that?
So you don't have to finish the calculation, like minus
Well,
5/14 times the vector.
yeah, I'm just going to leave it like that for now.
So that's enough. That's good enough. So that is the right answer.
Well, Well, this is not our answer because we really wanted the yellow one, right? We really wanted B3. We want this guy because we want it to be perpendicular to B1. What we just calculated is a scalar multiple of B1. So my B3 is my original B2 minus B2 hat that we just calculated. So my B2 was 1, 2, negative 3. No, it wasn't, my bad. My B2 was 1, 0, 2. Minus a negative 5/14 times 1, 2, negative 3. Okay, and I'm going to spare you the details, but this is going to be 1/14 times 19, 10, 13. So yeah, that's just, I found a common denominator and I did it. So don't worry about that. Computers do that for you, or calculators. Okay, so what I'd like to do now, so what we found is that my B1, which is 1, 2, negative 3, and this weird vector 1/14 times 19, 10, 13. This is an orthogonal basis for W. You should be able to convince yourself that if you take the dot product of those two vectors, you get 0. Okay. You can, in fact, ignore the scalar because scalars can be pulled out of a dot product. So I get 19 plus 20 is 39 minus 39, that's 0. So dividing by 14, it's still 0. And so, yeah, those are orthogonal. Okay, so pop quiz. Is it an orthonormal basis? Can anyone remind me what an orthonormal basis is? It's different from orthogonal.
It's basically when each vector is a unit vector.
Yeah, it's just when each vector is a unit vector. Okay, so there's my basis, right? It sits right there. Okay, so you got to check if those vectors are unit vectors. Thumbs up for yes, orthonormal basis, clapping for no. Not an orthonormal basis. Oh, actually, let me ask you one more thing. How many of those vectors have to be unit vectors? There's two vectors there. How many have to be unit vectors for it to be an orthonormal basis?
Just one?
Well,
Actually, all of them, right?
all of them have to be unit vectors to be an orthonormal basis. But if just one is not a unit vector, you know that it's not a unit, an orthonormal basis. Okay. So if you can find one vector in here that's not a unit vector, you know it's not an orthonormal basis. The only way it can be orthonormal is for both of those to be unit vectors. So thumbs up for orthonormal, clapping for not. Ooh, not getting a whole lot of response. Killing me here. How can you tell if this is a unit vector? How do you find the length of this vector? Does anyone remember how to do that?
The square root of every entry squared.
Yeah, it's just the square root of the sum of the squares. So I take 1 squared plus 2 squared plus -3 squared, and then take the square root of all that. And by the way, if you want it to be unit length, the sum of the squares has to equal 1, right? So all of those added together, well, they don't, right? Because I get 1 plus 4 plus 9. Clearly not going to be 1. So yeah, this thing is not orthonormal at all. So no, it's not. Okay, so make it an orthonormal. Pop quiz. How can I make an orthonormal basis? Orthonormal basis from it. Okay, so here's the schematic, right? Let me get my colors right. So B1 was blue, right? I got my B1 here. That's one vector. And then B3 was yellow. So that was perpendicular, right? So this is my B3. So I'll also tell you that this other one is not a unit vector either, even after you divide by 14. Okay. So neither of them are unit vectors. Notice that there are unit vectors in their direction though. Like I could take the unit vector in the same direction as these guys, and that would be an orthonormal basis. We called that normalizing vectors, and we get it just by dividing a vector by its length. Okay. So if you divide, right, if a vector has length 5 and you divide it by 5, then it'll have length 1. Or, you know, you multiply by 1/5, then it'll have length 1. So in this case, here we found the length of the first vector. And so that's going to be 1 over the square root of 14 times 1 to -3. Right? And I need a scalar multiple of this other vector, 19, 10, 13. So I'm going to put the scalar on the right. And the scalar is just 1 over the square root of the sum of the squares of the entries. So I don't have a calculator, and I just am trying to get the idea across, and I'm just going to write that scalar down. So it's just 1 over the square root of 19 squared plus 10 squared plus 13 squared. I wanted to remind you how to normalize a vector. If it's not length 1, you just divide it by its length, and this has to be length 1, okay? Same with this guy. I don't know what that value is. If I really cared, we could figure it out, right? The point is you can always take any orthogonal basis and turn it into an orthonormal basis. Just by dividing each vector by its length. That's it. Done. So maybe I should even write that down. Divide each basis vector by its length. Okay. Any questions about that?
So how come it's the square root of 14? I'm trying to wrap my head around that.
Oh, I got that from up here.
Oh, okay.
Does that make sense?
Yeah.
Okay. Yeah, just square each entry, add them up, get 14, and then take its square root. Okay. Other questions? A couple of facts here that I just want to highlight. Fact, if U1 to UN is an orthogonal basis, for W, then for each Y and W, you can easily write Y as a linear combination of these guys. Okay. You know, when we first introduced the notion of a basis for a subspace, I started with a vector in that subspace and I said, write it as a linear combination of the basis vectors. And then that gave us the B vector, you know, B coordinates for it. And that was a fairly consuming task, actually, because we set up a linear system and we had to row reduce and all this kind of nonsense. But if the basis you have is orthogonal, then finding the B coordinates of it is much easier. For each Y and W, we have that the vector Y is just Y dotted with U1 over U1 dotted with U1 times U1. And it's the same for each of these. So Y dotted with U2 over U2 dotted with U2 times U2. And it goes all the way out to the nth vector, Y dotted with UN over UN dotted with UN times UN. Notice that each of these, this is the projection of Y onto U2, right? That was our formula for the projection of Y onto U2. You put U2 everywhere except that one slot and you just stick a Y there. Okay. So that's a nice feature of orthogonal bases. And then so for example, oops. Well, sorry. Let me just say it this way. So if I have 1, 3, -3, 1, this is an orthogonal basis. Suppose this is B. This is an orthogonal basis for R2. Write E1, which is just 1, 0, as, or actually, let me write it this way. Find the B vector for E1. Okay, so that notation should be familiar, right? And according to this, that means I just have to first write E1 as a linear combination of these guys, right? And then the weights in front of those become the B coordinates for the B vector. But we know this is an orthogonal basis, so we can just use this formula. We can project E1 onto both of these, and that writes it as a linear combination. Okay, so E1 is just going to be, 1, 0 dotted with 1, 3 over 1, 3 dotted with 1, 3 times the vector 1, 3 plus 1, 0 dotted with negative 3, 1 over negative 3, 1 dotted with negative 3, 1 times the vector negative 3, 1. So that just gives us, so remember that the denominator is just the sum of the squares of the entries. So that's going to be 1 plus 9, so that's 10. So this will give us 1/10 times 1, 3. And over here I get minus 3/10 times negative 3, 1. And so that means the B vector is just 1/10 negative 3/10 tenths. I'm sorry. And that's it. Because the B vector is just the coefficients when you write E1 as a linear combination of those. Any questions about that? Okay, and this, you can draw, I mean, there's, so the two vectors, I just made that one up on the fly. So let me come back. The two vectors were 1, 3, right? So this is one of my basis vectors. And then negative 3, 1. So that's orthogonal. So those are my two basis vectors. This was my B1. This was my B2, right? And the vector I'm looking to project is this one, 1, 0. So I just project it. Oh, no, wait. Let's do a different color. So it's this vector plus that vector, right? And this is the negative 3/10 times B2. And this is the 1/10 times B1. Okay. And this is my E1. Okay. All right, any questions about that example?
I had a question.
Yeah, go.
For the previous page, when you used 1, 0 to multiply to 1, 3 and then 1, 0 to multiply negative 3, 1, is there a reason why it's specifically 1, 0?
Yeah, that's E1. Both of those are, that's what I mean when I say E1. E1 is the vector 1, 0.
Oh, okay. So we just assume that E1 is 1, 0, or
Yeah, always. Yeah. So that, and that's standard, like when I say standard basis vectors, I mean the ones that have zeros everywhere except one slot, and then that one slot it has E1. Sorry, in that one slot it has a 1. So if I wrote E4 in R5, so I got to tell you what dimension it's in, then it's the one that has a 1 in the 4th slot and zeros everywhere else. Does that make sense?
Yeah, I just wanted to make sure.
Yeah. And the one, I will say that I'm trying to be careful. The one weird thing is that this is horizontal, right? But remember, this is really E1 transpose dotted with B1 or times B1. Okay. Anyway, yeah, it's weird. There's a lot of weird notation. But that's why I wrote it horizontally there when I've been ultra careful not to. Any other questions? Okay, so I've been instructed, or I guess, so that's all I'm going to say from chapter 6. And for the rest of the semester, we're going to talk about parametric curves and surfaces. And this, it's not from the book. There are some sections in the book that talk about Bezier curves and Bezier surfaces. And we may get to that point where we can talk about those. But I think it would be helpful to have a little bit more. So I think it just would be helpful to have a little bit more background on parametric curves and surfaces. So I'm going to be augmenting the material from the text. So first we'll talk about parametric curves. And let's just start in R2, so in the plane. So let's talk about curves in general. You've run into curves in the plane in a lot of different ways, okay? You've run into it in terms of graphs of functions. You know, something like y equals x squared, and then everybody knows, oh yeah, that's a parabola, right? That's a nice curve in the plane. Solutions to equations, solution sets to equations. And here, something like x squared plus y squared equals 1. Anyone have any idea what shape that is? What is the graph of x squared? Yeah, it's a circle. In fact, this is the unit circle, right? It's centered at the origin and radius is 1, right? So if you throw in your axes, you get something like that, right? And you've worked a lot with those in calculus. You worried about graphing, you know, finding maxes and mins and inflection points, and when is it increasing, decreasing, concave up, concave down, all that stuff, right? Okay. There are also another way, a third less common way, although some people do it, is parametric curves, okay? And these are given by where each coordinate, both x and y, are given as a function of a third variable t, right? So sometimes it's given as x equals, for example, x equals cos t, y equals sine t, and t is called the parameter. These are called my parametric equations for x and y. for X and Y. And T is the parameter. And usually you will have to give limits on your parameterization. Okay. You'll have to tell me what values of T you care about. All right. And sometimes I'm just giving you more notation. You'll just have something like the curve, you'll just write it in point format, right? At C of T equals cos T sine T. So more generally, a parameterization, a parametric curve is given by parametric equations. X equals some f of t, y equals some g of t, and together with limits on the parameter. So t is between some a and b. And the a and the b could be infinity. And there's two ways I like to think, two different ways I think of the parametric curve. I can think of the X equation as telling me, I think of the variable T as time. And this just tells me the point that a ladybug crawling in the plane is at time T. So X is the horizontal position of the ladybug at time T. Y is the vertical position of the ladybug at time T. Okay. I used to say ant, but somehow ladybugs are just a little bit nicer. You know, you just don't get the same creepy feeling that you get from ants. Anyway. Okay. So that's one way to think of it. Think of a parametric curve as just telling me where this ladybug is crawling at time t. This is the position of the ladybug at time t. Another way to think of it is actually, so I can think of C of t equaling cos t sine t as the position of a ladybug crawling in the plane at time t. That's one way to think of it. Another way to think of it that is also useful is to separate the domain, to think of the t between 0 and 2 pi. This is my t interval, right? And C, the parametric equations are instructions for how to bend, twist, stretch that piece. Think of this as a piece of wire. And C is instructions for how to bend and twist it and put it into the plane. So I can think of this as a piece of wire. And then C is instructions for bending, twisting, stretching the wire into the plane. Okay. And by the way, I will just, let me color code this just because I can. So it turns out in this case that C is the unit circle. And in fact, it's a unit circle oriented counterclockwise. So not example, but in fact, this parametric curve, so C of t equals cos t sine t, for t between 0 and 2 pi, parametrizes the unit circle counterclockwise. So from now on, I'll say CCW for counterclockwise, okay? And I want to try and give you a convincing argument of that. And the one, you know what, I'm just going to give you one convincing argument of that. And that is, suppose I make an angle T with the positive x-axis. Does anyone remember their unit circle from trig? If this is the point P where it intersects the unit circle, what are the coordinates of that? So let me say this one more time. Suppose I take a ray from the origin and that makes an angle of T with the positive x-axis. I extend that ray out that makes an angle of T with the positive x-axis, and I look at where it intersects the unit circle. Does anyone remember what the x and the y coordinates are?
Sine theta and sine theta.
Yep. Cos theta and sine theta, except for I use t this time instead of theta. So this is just cos t sine t. But look, that's what we said C was. C of t, so where this ladybug is crawling at time t is precisely this point here, cos t sine t. The point of intersection of the unit circle with a ray that makes an angle of T with the positive x-axis. So there you go. This curve just parametrizes the unit circle, and we go counterclockwise because we always go with the positive x-axis. Okay. Let's do some more examples of parametric curves, okay? More examples, because it takes a little getting used to. I want to use linear algebra for one. So again, in the plane, suppose V is the vector 2, -1. Then I could let C of t just be all scalar multiples of that. And I mean all, so t goes from -infinity to infinity. To use the, or to use this other point notation, C of t would be the curve 2t -t for t between negative infinity and infinity, right? So I got my v, my vector v is 2, -1. That's my vector v. And now what happens to that if I take scalar multiples of it? What happens if I look at all scalar multiples instead of just v?
It's just a line
That's
both
just
ways.
a line, yeah. That's just a line that contains v, right? So now this is my c. So in this case, this is the line through the origin, through 0, 0, containing the vector v, okay? So here, let's generalize this a little bit. Parameterize the line through, say, the point -1, 2, containing v. So -1, 2 goes to left 1 and up 2. So here's my point -1, 2. And I want the line that contains v, right? Now, I think I've mentioned this before. We haven't done a whole lot with it, but like in physics and in multivariable calculus, two vectors are the same if they're the same length and direction. It doesn't matter if they have the same initial point or not. So this vector, both red vectors are the same. So I want that line instead. Now let me just give you a suggestion. To get from the origin, I just have to translate by -2, 1, right? To get my vector v up to where I want it to be, I just have to add -2, 1 to it. So how should I get the whole line up to here? And let me give this a point and name. Go ahead.
Do the same thing.
Just add p to it, right? So if this is my point p, I'm just going to add p to every vector, right? That's the same as just saying translate the entire plane by this one vector p. So the idea is just add p to the above. So now my C1 of t is just going to be -1, 2. Okay, which is my p plus t times 2, -1. So that we can just write it in vector form as -1 plus 2t and 2 minus t. Or if we like points instead, C1 of t is just the first coordinate is -1 plus 2t, and the second coordinate is 2 minus t. what I'm hoping is that since we've done so much linear algebra and adding vectors and looking at pictures, what I'm hoping is that that makes sense to you. We've been translating things. We've been doing lots of stuff that if I wanted all points on this line instead, I just keep adding P to points on that line to get a corresponding point on this line. Okay, and what this generalizes then. So notice the information we were given. We were given a point on the line and a direction for the line, right? So it's not like in, you know, before you needed point and slope, right? Or 2 points or something like that. Now I want a point on the line and a vector in the line, okay? So more generally, given a point P on the line and a vector V in the line, so I'm not going to color code it. There's my point P and there's my vector V. Then to parameterize this line L, you just take the P plus T times V. Then C of T equaling P plus TV between negative infinity and infinity parameterizes the line. Okay, so quick example. Parameterize the line through, say, 1, 2, and 5, 6. I need a point on the line, and I need a vector in the line. If you can tell me a point on the line and a vector in the line, then we just use this formula to find parametric equations for the line, okay? So it doesn't hurt to just sketch a quick pick, okay? So 1, 2, that's this point here. 5, 6, so that's 5, 6-ish, I don't know, somewhere like this, right? And I just want the equation, or I want to parameterize the line through those 2 points. Okay, pop quiz. Can you tell me a point on the line? Yes is the answer. In fact, how many points can you tell me that are on the line?
As
An
many as
infinite
one, I
number?
guess.
There's 2 of them, right? It's 1, 2 is on the line and 5, 6 is on the line. So I know, let's just pick 1, 1, 2. Okay, excellent. But it doesn't matter. You could have picked either one, okay? So, but you do know 2 points on the line. How about a vector in the line? And I'm going to ask you just to go with your gut here. You know, the idea is to be able to draw some vector that lies right on the line. Like, where should I draw it? how can I use the given information, the 1, 2, and the 5, 6, to find a vector that lies in the line?
Just make a vector between the 2 points.
Yeah, just go from one to the other. Okay. Okay, I messed up, but yours is going to go right on top of the line, right? If it goes from one to the other, that's going to be my vector in the line. Now, I've said it a couple times, but we haven't really done it that often. How do I find components for this vector? If I know the terminal and the initial point, it's always terminal minus initial, right? So it's 5, 6 minus 1, 1, 2. So that's 4, 4, is it? So a vector in the line is 4, 4. And we just write down the formula, right? So I know that to parameterize it, I got to go through 1, 2, and I got to add scalar multiples of 4, 4. So 1, 2 plus t times 4, 4. So that's going to be 1 plus 4t, 2 plus 4t. And that's it. Any questions about that?
So what is the vector 5, 6? Which one is that?
5, 6.
Do you draw it? Yeah.
5, 6 will go from the origin up to 5, 6. And the vector 1, 2 will go from the origin up to 1, 2. So I definitely was not drawing that. You can think of points in the plane as either as a point or as the terminal point of a vector from the origin. And I'm definitely doing both in this process. I'm thinking of a point in the plane two different ways. On the one hand, I think of it just as a point, and on the other hand, I think of it as a vector connected to the origin. Any other questions? Okay, so now I want to go a little bit backwards, right? So we know how to, well, actually, no, I want to do one more thing. Notice that this vector v was like p minus q or something like that. So to parameterize the line segment, from P to Q. Okay, so let's just have, suppose we have a line segment. We know its initial point, we know its end point. And I just want to go from P to Q. I don't want to go the whole line, you know, T between plus and minus infinity. I just want to do that. I know that this vector is Q minus P, right? It's terminal minus initial. I also know that to get it to the right starting point, I got to add P to it. So the parameterization is going to be, first you add the green vector, and then you take scalar multiples of Q minus P. And what I'm looking for is limits on T. Now, I should have done this on GeoGebra, but I didn't. Okay. The idea is difference. If T is 0, where is this parameterization? So what is C of 0? If I plug 0 in for T, what point am I at?
Just P.
Just P. So when T is 0, I'm starting at P. And remember, I want to start at P and end at Q. Now, if I plug a half in for T, I'm going to be halfway out on this vector. If I plug 3/4 in for T, I'm going to be 3/4 of the way out on this vector. If I plug 1/4 in for T, I'm out 1/4 of the way on this vector. How do I get all the way to Q? What do I got to have T equal so that I'm all the way at Q?
Four.
I'm sorry, I didn't hear you. Let me write it another way. I could think of just solving this equals Q. Like, when is that going to be equal to Q? Well, these are all vectors, by the way. T is a scalar, right? So this is going to be P plus T times Q minus T times P has to equal Q, right? So this tells me that 1 minus T times P plus TQ has to equal Q. What value do you plug in for T to get Q out? This is not a trick question. What number do I plug in for T to just be left with Q?
0.
One.
I mean 1.
1, yeah, you just plug 1 in for T. So for T between 0 and 1, this parameterizes that line segment. And typically, to be honest, this is usually how you'll see it. And this is actually what's called a Bezier curve of the first order. But C of T equaling 1 minus T times P plus T times Q for T between 0 and 1 parameterizes the line segment from P to Q. So let me highlight that in red or something, because, oh, that's not highlight, is it? And that's not red, is it? So let's highlight that in red. That answers your question of parameterizing the line segment from P to Q. But I want this to, you should grab a cup of coffee sometime and think about why putting a 1 here makes sense. Because 1 means I go the full length of this blue vector, right? When I plug a half in, that means I go half the length of the blue vector. When I plug a quarter in, I go a quarter of the length. When I plug -1 in, that means I go the opposite direction, 1 length. But if I want to end up here, I got to go one full vector. So T better be 1. So that's why the upper limit should be 1 to make that work. Okay. there are other cool, okay, I should do, here we go. Let's do a couple of more. Here's a pop quiz. Find a vector in the line C of t equals 2 minus 3t, 4 plus 2t. T between negative infinity and infinity. Actually, a point on the line. And a vector in the line. So now I'm going backwards, right? Before, way back here, I started with, if I know a point on the line and a vector in the line, so if I know that information, I know that this parameterizes the line. Now I'm starting with the parametric equations and I'm asking you to find P and V. Okay. So how can you find the point on the line that I used? This is, the point is the constant. It doesn't have the parameter there. The T is the parameter, right? And the point is the constant. So it's just C of 0. Like if I wanted to know what C of 0, I plug 0 in for T and I get 2, 4. And that's my point P. So the constants tell you a point on the line. A vector in the line just comes from the coefficients of T. Right here, the vector in the line was 4, 4. That was just the coefficients of T in the parameterization. So here, I just look at the coefficients of T, and I get that the vector is negative 3, 2.
Okay, perfect.
Does that make
I'm gonna
sense?
go just like do some errands of my own and then come back. I just wanted to make sure that I wouldn't be late.
Any questions about that?
Anything like that. Cool. Yep, I will. I'm just curious, do you think that I can leave my car
Hang on just a second.
where I parked?
Anyway, yeah, so any questions about that example? All right, so let me do one advantage to this, which we have to quit here in 5 minutes. So I wanted to show you one advantage to parametric curves. And that is that you can do 3-dimensional curves very easily. So parametric curves generalize to arbitrary dimensions. And so I'm going to show this on GeoGebra, but I just want to look at C of t equals cos t sine t t for t from negative infinity to infinity. Okay. So those are the parametric equations that I'm going to look at. And you should grab GeoGebra real quick. And put it in 3D. Okay, and I'm going to stop the share from this. And start the share from this. So that you can see my GeoGebra. And now you just say curve. And our parametric equations were cosine of t, then sine of t, then t, and then t goes, and then the parameter is t. So you got to write t again the second time you write it. And then let's just go -5 to 5, say. And what you get is this helical spiral that goes around the z-axis. So if you look straight down the z-axis, you just get the unit circle. And the reason that is because if you ignore z and you just look at the x and the y, that just gives you the unit circle. The z coordinate then just starts wrapping you around, or lifting it up, right? So the x and y coordinate wraps it around the z-axis and the z coordinate lifts it up. So if you went from -10 to 10, it would just be like a slinky stretched, right? And here it doesn't even go that far because it would just keep rotating around. But again, as you look down the z-axis, then all you see is a circle and you're just stretching the slinky. Let me give you one other example that I have written here. Okay, here's an example of a curve that has fairly complicated parametric equations over here on the left, right? And that turns out to be a knot in space. It's knotted, sort of loops around, and you can see where it kind of goes over here and then under there. It's called a trefoil knot. There's exactly 3 places where it crosses itself here. And it's also an example of what's called a torus knot because it actually lives on a torus in 3 space. So if I get rid of the plane, you can see that this knot just lives on a torus. And knot theory is what I study, and that's why I wanted to show that. But the real point is that if you want to talk about curves in space, then parametric equations are the way to do it, okay? Because you just tell me where that bug is. So the interpretation is this first equation is where the x coordinate of the bug at time t, this time the butterfly is taken off and it's the ladybug is taken off and it's starting to fly, right? This is the x, y, and z coordinate position of that ladybug as it's flying. Okay. All right, any questions? Okay, we'll come back next time and keep talking about parametric curves. Otherwise, good luck on the quiz, and we'll talk to you guys tomorrow, or next week, sorry. Have a good weekend.
See you.
See ya.
Yep.
If you go surfing, careful with the sharks and the waves.
Yes, I will do both.
Enjoy the weekend. Bye-bye.
Bye. Do you guys have questions? Any questions, Ethan?